Hello everybody, Stoner Dave here, and today we're going to do a lesson. I don't normally do lessons, I normally just talk a little bit and maybe we'll show a couple examples, but we're going to do a lesson so that you can fully understand how to calculate impedance. Detroit Wrecker is under the impression that, seems to be under the impression that when you're dealing with impedance, that you just take the resistance and add the reactance to it, and that's not very accurate at all. It's not much harder than that, but there is a bit of a process. So, like I said, we're going to look at a few different things, right? So, we're going to look at how a signal responds going across a capacitors and inductors and resistors. So, I have here, I believe this is a 100 millihenry inductor. I will measure it just to make sure. With the old LCR meter. Oh, it's 100 microhenries. My apologies. 100 microhenries. Okay. And I want to use a capacitor not very different, so this should be a 100 microfarad. Let's measure that to make sure as well. Yeah, it's 100. It's not exactly 100. There's a variance because of tolerances, but 88.5 is not too bad. And for the inductor, like I said, it is 98.1. Okay, but we're not going to be there just yet. I've got to go over a few things before we start getting into impedance. So without further ado, all right, folks, let's get started. So to understand impedance, you first have to understand resistance. Resistance is the primary factor of impedance. In fact, if you have a perfectly matched system, resistance should be the only factor of impedance that you will be able to see. So, without further ado, let's take a look at the first example of resistance. Simple voltage divider. This here is a simple voltage divider. We have two resistors, both of which are 100K. They're in series. And what we should be finding is here at this junction, we should be getting a voltage about half of the source voltage. The resistors aren't exactly the same, but they're close enough that we should get something that's fairly close to half of the value. So turn on the power. Our power is 5 volts. Turn on our voltmeter to our volt setting. Take our black probe, put it onto the negative terminal. Our red probe to the junction. And we have 2.53 volts, which, if I can get this on here, if I can get it on there. What the hell? It's a lot harder to do with one hand. Ah, there we go. 5.06. So, yeah, exactly halfway between. Now, what that is a demonstration of series resistance. Total voltage of the whole system, 5 volts. You see that half that voltage dropped across the first resistor, the other half volt dropped across the second resistor, getting us down to our ground, which is 0 voltage. Now, if I take another resistor, say another 100K, and put it in parallel with that, that is that both these resistors start at the same place and end at the same place, well, the resistance should be cut in half. There's a formula that you can use. Let me go ahead and write that down for you. So, first of all, we have resistors in series. Which is just like this. We have the RT, that stands for total. It's equal to the R1 plus R2 plus however many resistors you have. So Rn. Rn means just R times the plus the number of them. So series resistors just add up together. When you put them in parallel, though, something happens. Because you don't add the resistance, you're adding the conductance. It's another factor, one that's not really talked about a lot, but conductance is equal to 1 over resistance. It's the inverse of resistance is conductance, its ability to conduct. When you put resistors in parallel, the number of routes that they can conduct along increases, so you're adding conductance. Since resistance is the inverse of conductance, you have 1 over RT is equal to 1 over R1 plus 1 over R2 plus plus 1 over R, however many they are. So your formula looks like this. Now, there's lots of ways to do this, but what I like to do is I go 1 over R1 plus 1 over R2. And so if we take this, we put 1 over the beginning and then 1 over blah, 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 put some parentheses and do the 1 over whatever plus the 1 over whatever plus 1 over until you get to your total. You get it. So what I'm going to do is I'm going to grab another 100K ohm resistor. Try to get one that's the same type, so we should be closer to value, because lower levels of tolerances and all. I'm going to put this in parallel with R1, so just so I can do a quick calculation. So it's 99.4, so it's a bit lower than the other two, but shouldn't have too much of a impact over that. So now we have half the resistance for our first half. So the voltage drop over that should drop a pretty decent amount. Let me see if I can do it in my head. So it's about 1/3 of 5, right? Well, half, 1.5. Okay, so looks like we have 3.39 volts going across our second resistor now instead of 2.25. So yeah, dropped it down to about a third, which is about what we expected. You know, the second resistor is twice as much as the first one. It's about what we expected, right? And that's parallel resistance. Each time you put a resistor in parallel with it, it drops the resistance by a factor. If they're all the same, you can literally just divide by the number of resistors. But if you have different resistances, you have to go through this whole formula. So this is just a 1K resistor in parallel with a 1K resistor. So we have about 500 there. So if we were to do the math, we have, let's see, 500, so 1K divided by 1.5 times 5. Let's see, I'll just do this here. $3.333, and our voltage 3.39. And doing it the other way, we have 0.5 over 1.5 equals 1.67 and 1.656. Very close, right? Approximations. And that's parallel. Now, somebody asked me if I understand series parallel as if that were something complicated. So just going to draw that out for you, what a series parallel looks like. So this is what a series parallel looks like. You have a resistor here and a resistor here, both in series. And these are in parallel with a resistor here and a resistor here, also in series. So you have series parallel. Now, people think that that's hard to calculate, but it's really not. See, let's say we have this is 8 ohm, this is 8 ohm, this is 8 ohm, this is 8 ohm. Well, we already know from series that the series add up. So this is the same as 16 in parallel with 16. Like this. Okay? This is equal to this. And looking at what we just learned from the parallel, this is equal to just one 8 ohm resistor. Series parallel. That's how it works. That's why it works. You're adding the resistances and then you're adding the conductance. That's all it is. It's very simple stuff. It works for speakers, it works for resistors, it's used in a lot of things. Something that a lot of people aren't too familiar with is when you take something and you do like this. Alright, and we're going to have 8 ohm here, 8 ohm here, 8 ohm here, 8 ohm here, and I'll put a 16 ohm here. So this is not series or parallel, and a lot of people get fucked up by that. And this is probably the most commonly used circuit in all electronics. We're not going to go into it here. It's way too advanced for you. But that's series parallel. All right, so that's DC resistance in a nutshell. So let's start looking at impedance, okay? So for impedance, I'm going to do something a little different. I'm going to take a 1K ohm resistor, and I'm going to put that as kind of a lift from ground. So what that's going to do is give us a place where we can measure the output signal. And it's not really anything for any other reason except for to be able to see how the signal changes across different levels of impedance and resistances. So I have a 1K resistor here, and I'm going to use a 10K resistor just so we can look at the resistance aspect. So $10K resistor. Reason why is we're not so concerned about the voltage drop, how much it is. We already know it's going to be a resistor. It's going to be the same as if it was just a DC circuit. So 10K, 1K, we'll see 10% of voltage drop here, 1% there. So we should see 4.5 volt drop across this. Of course, this being a AC circuit, the drop will be visible. Well, it'll be harder for us to see on the scope because, well, scope isn't going to give us a readout like that, right? So I'm gonna do channel 1, which will be the yellow line on our scope, is just going to read the signal coming out of our function generator. Channel 2 is going to show us what it looks like on the other end of the resistor. So I'm going to turn my scope on here, turn on my function generator. All right, so got a good view up there. Let me go ahead and show you. Okay, so this is our signal, right? You can see I've got channel 1 set to 2 volts per division, channel 2 is 1 volt per division, and it's not a very big signal coming out. So turn that up. So it is approximately set up so that you can see. I'll pull up our measure channel 2. Add that. So 500 millivolts peak to peak on channel 2. And let's see, channel 1. Do that as well. So you can see there's a bit of a fluctuation, but 5.2, 5.2. But you can see they're in phase, and there's a pretty substantial voltage drop, right? 90% of it is dropped across channel 1, channel 2, so you're only getting 10% of it right here. That's all that is. It's 10%. Makes sense, because our lift is about 10% of our load there. Now let's take a look at what happens when we put other passive components. Talking resistors, inductors, and capacitors. So first, we're going to take this resistor and we're going to replace it with an inductor. All right, for this next part, we're going to replace the resistor with an inductor. All right, so still going to use the 1K ground lift there so that we can actually measure this. And where is my inductor? Inductor. I guess I can get another one. Got more than one. So, looks like this is 100 millihenries. I'll pop it onto my LCR meter to measure the component here. Make sure we've got something on there. And 96.2 millihenries. Pretty close to what we were expecting, right? So we'll put this in series with this resistor. Hook our current source on there and our there we go. All right, so we've got the signal up here. I'm going to show it to you in just a moment. But there's going to be a few things that you'll want to pay attention to. So real quickly, let me go ahead and change the view for you. All right, so here we are seeing our signal through the inductor. You'll see the main source is the yellow one. That's our channel 1. This is what's coming out of our function generator. Channel 2, this purple line, is what's coming out of the inductor. This is our output signal. So you'll notice a couple of things. Number one, it's slightly smaller than the source. Not a lot, only slightly. You can see what that is. Now, you wouldn't expect it based on what you see with the DC resistance of this inductor. It's a very small, virtually zero. But what we do see is that there is kind of a phase shift here, right? Phase shift and a little bit of a voltage drop. Now, this is what impedance really is. It's this phase shift and the voltage drop. Now, this voltage drop isn't real power being consumed. This is apparent power being consumed. That's why when we calculate the reactance, we calculate it the way we do. Now here you'll see the voltage. Here we have our peak to peak, 5.2. And here our voltage peak to peak, is that right? 504 millivolts? Wow, it seems like it's more than we thought. Oh, look at that. It's 200 millivolts. So let's go to at 2 volts. So here you see voltage drop. It's quite a bit, right? And that's apparent power loss. Not real power loss. This inductor isn't going to get very hot from this signal going across it. But it appears to have a lot of impedance. Of course, this is at 10 kilohertz, so it's a pretty high frequency, above the audio spectrum, so to be considered, you know. But quite a bit. Now, there is a formula to calculate the reactance of an inductor. I'm going to show you that right now. One moment. All right, so like I said, there is a formula to calculate the reactance of an inductor. Now, the letter L is used for inductors. There's several reasons why, depending on which area of electronics you're dealing with. Some say it's because it leads the current, some say because it lifts the signal. Doesn't really matter why it's called L, it's just called L. So when we're talking about reactance, the variable used is X. So there's XC, which is capacitive reactance, and there's XL, which is inductive reactance. So XL is equal to 2 pi times the frequency times the inductance. So something that looks a lot like this. So for this inductor, we're going to just round it up to 100 millihenries. So we have 2 pi times 10K times 100 millihenry. That is equal to, well, my math isn't so good that I can just do this in my head, but got a handy dandy calculator right here. And there's also, when we start talking about current and everything and adding it, there's what's called a J factor. So I'm going to put that in there as well. And that's actually a vector. So it got a little hat on it. Looks like this. Let's see the little J right there with the hat on it. Because it's a vector. It's a unit vector. So understand that that's what the little J is there for. So when I write this down, it's going to have the ohms and the letter J with the little hat at the end of it. That's okay. You don't have to know exactly what this J factor is. Just understand that it's because it's reactance rather than resistance. Resistance is treated as as kind of a linear thing, right? Whereas reactance has, well, it's a phase angle, right? It determines a phase angle. When you add the real resistance with the reactive, you get an angle going between them. We'll talk about that in a little bit, I promise. All right, so we have 2 pi times 10K times 100 milli times the J factor. So 6.283185307 K ohm, right? Plus the J times the J factor. So let's just write that 6.28 K. with the J at the end so that you can see its reactance. Neat. Now, like I said, we have this 1K resistor here. So if we wanted to do the total impedance of this whole thing, what will we need to do? Right? Now, if you're like Detroit Wrecker, you'd probably be like, just add the two together. Right? But no. You can't just add them together. It doesn't work like that. As much as I'd like to be able to say it does, it doesn't. And my voltmeter here does have an AC voltage detector on it. So I can actually go through here and we can see the AC voltage across the entire thing. So we start at the beginning. We have why isn't this measuring my voltage here? I should be going up to 5 volts. Scope's showing the 5 volts there. Right. It's not giving me a good reading. Really don't like this meter for anything besides DC voltage. It's just not very accurate. I mean, at large voltages, it seems to work pretty good. I've plugged it into a 120 volt supply and it comes out 120 volts. So it's 1. So it's giving me the right ratio, but it's not giving me the right numbers. So screw that. What do I expect from a $10 multimeter, right? Definitely should consider getting a new one, but just haven't had the time or the space. But looking at this here, before I tell you how to calculate it, I'm going to go ahead and do the calculation based on the approximation of the 1K here. So there we go. And we do bless me. So what we end up with is approximately 6.2 K, which is mostly inductive. 6.2, so it's a bit less than what we were coming up with the inductive reactance, right? It is showing up as being mostly inductive, but again, it's still less than the 6.28. Not a lot. And of course, these are K, so 6,283. So now we have 6,200, approximately 6.19987, approximately. Just approximately. We don't need to go more than 2 decimal points because you start getting into too much, you know. You start getting into the weeds about stuff. And we don't need to be that precise with really anything, right? But 6.2 K inductive. Now, there's a phase angle. I talked about the phase angle, and we can actually use the same process. We just have to change the way that we look at the answer. So on my calculator, there's a mode here. And what I'm going to do is I'm going to change the way that we look at this, and we're going to change it to the real to n times a phase angle. And then we're going to look at the same exact equation. 1K of resistance plus 6.28K of reactance. And we get 6.1998, so 6.2. And we have a phase angle of 1.57 radians. Radians are a kind of a way to measure the angle. It's kind of like degrees, only different. There are only 2 pi radians in a circle, and there are 360 degrees in a circle. Same thing, just a different way to look at it. So 1.57 is a huge shift, and if we look at the way that the frequency is lining up, we can see that it is almost a full 90 degrees. 180 degrees would be going from one to the other. 90 degrees is about halfway, and 360 is all the way around, so it'd take it all the way around. It's going from almost from one peak to the other peak. It's going from the high peak to the low peak. It's almost shifted 90 degrees, which would be about a quarter of a turn. 180 degrees would be a full shift, and there are ways to calculate it and measure it with the scope, and I'm not going to get into all of that with you right now, but we can by changing the mode one more time, right? I go in and change it from radians to degrees. Hold on one moment here. All right, that should stop that. So I'm going to change from radian to degrees. And we're going to plug in the same equation. So 1K plus 6.28K and that is reactance, and we hit enter, and it's about 90 degrees. So I have 6.2K to about 90 degrees. It is an approximation, right? Because this 1.5707963227, it's approximately half of pi. Pi being 180 degrees, half pi being 90 degrees. It's not quite 90 degrees. It's more like 89, but it's so close to 90 that the calculator rounds it up to 90, because when you're dealing with degrees, you only get so many units of precision. So 90 degrees makes sense. It looks about right. So there we go. There we have it. You can see that we have got a good amount of impedance here, and the voltage drop is pretty accurate, you know, 6.2K out of 7K, you know. It's all good and fun. But we're not getting the full picture. So next, we're going to take a capacitor. I think I got a 100 microfarad capacitor right here. Let's make sure it's 100. It says 100. Let's measure it out. .5 close enough. So let me go ahead and change this over and take a look at that. We're not going to change the source. We're going to still have the same 10K frequency. We're going to have the same 5 volt peak-to-peak source, but we're going to change from a inductor to a capacitor. Capacitors show up as being virtually an infinite amount of DC resistance. The inductor shows up as virtually 0 DC resistance. But as we can see with an alternating current, this inductor is showing up 6.28K. So let's see what this capacitor does. All right, so I've changed it over to the capacitor from the inductor. My function generator is giving me a little bit of a fluctuating signal, but I think we'll be okay with that. There we go, kind of stabled out a little bit, loose connections and all. I think I got it pretty solid now. So let's take a look at the signal here real quick so you can see what we got going on, and we'll look at the math then. All right, so here's the signal through the capacitor. Now, you'll see that we've got a much larger signal going on here. Looks like a little bit less of a phase shift, but of course we'll want to look at the math to determine all of that here. But it looks really like what I was expecting, you know. Should be seeing a bit less reactance from this because we're dealing with a capacitor. And of course, there's formulas to determine the amount of reactance and the phase shift. So let's take a look at those and see what we come up with. All right, so I put the the inductor in series with the capacitor. Now, what that's giving us is a unique little output there. So we've got the capacitor, which shows up as having a very small amount of reactance, and the inductor, which has a very large amount of reactance. Let me just write down that total for us here. So so what was it? Negative 159.15. Sorry, my pen is going out. What the hell? It'll scribble, but it won't write? What the hell? All right, maybe another one. All right, so we got the inductor is showing at 6.28K ohms with the J factor. The capacitor is a negative 159.15 milliohm with a J factor. Now, this is showing us really the same thing, right? It's got both of these being added together. But it's not giving you what you would expect. So let's take a look at the output and see if you can figure out exactly what is going on with this thing and if it makes sense to you. Okay, so this is the output with the capacitor in series with the inductor going into our lifting resistor. As you can see, there is a substantial amount of voltage drop and a substantial amount of phase shift. Now this is mostly inductive, so the phase shift is going this way. If it was more capacitive, the phase shift would be going the other way. Now, how much of a phase shift do we have? Well, we'll have to do some calculations to determine it. There is a way to measure the distance between the peak and using the frequency, but that is a lot harder than just pulling out the calculator and adding these things together. But I'm going to go ahead and pull out the calculator and add these things together for you so that you can hear it first. After this, I will we're going to switch the capacitor and the inductor so you can see how that looks on the scope and if there's a difference. All right, so the way we calculate the inductance and capacitive reactance along with the resistance is really the same way we've done both of them. Now, the reactances will add together. Well, one's negative, one's positive, so it's technically going to be subtraction, but you'll see that it works out to give us something very similar to what we'd expect, right? So we're going to add these. First, we'll take our resistance, which is still 1K, right? And then we're going to add that to the sums of our capacitive and inductive reactances. So our capacitive was, well, we'll do the inductive first since that is what it is. 6.28K. And next is our capacitive, which rather than plug this in here, I'm going to actually put the formula in there because, well, it's more fun to actually see it work out that way. So I'll put a parentheses 1 over 2 pi times 10K times 100 micro. That and that and that. All right. So check this out. Our total, and my scope is finally settled down, and this is actually matching. We get 1.0009847K with a phase angle of 179.9 degrees. Basically just a hair under 180 degrees. And I'm looking at the scope and I'm seeing that the peak is almost lined up directly over the other peak. I'll give you another view of it in just a moment. But as you can see, it is definitely there. And the phase angle, it's right there. And I'll also put this into a format so that I can show it as both with and without the angle included, so you can see the two different ways to read these. It is imperative that you understand the phase angle is just the difference between where the peak of the incoming signal is and where the peak of the outgoing signal is. So we're measuring it across this resistor. That's why we have what we have. We're using the total resistance of the series system. It is...
A system is a group of interacting or interrelated elements
I wasn't
that act
talking
according to
to
a set of
you.
rules to form a unit.
Sorry, my computer thinks that I'm talking to her while I'm talking to you. She's got a mind of her own, really. But the system here is got the capacitor going into the inductor, going into the resistor. Now, I said we're going to switch the places of these two to see if there's a change. So I'll show you the signal again before I switch them over so you can see exactly what's going on here. Know that I'm not trying to play any hocus pocus games with you or anything like that. Understand, this is just the way that we do things. All right, so I've switched the order. The inductor is now in front of the capacitor. And wouldn't you know it, the signal looks exactly the same. No changes to voltage drop, no changes to phase angle. It's exactly the same. Even with the fluctuations that come with my signal generator, everything still the same. So let you take a look at it one moment here. All right, so here's the signal with everything changed. As you can see, it's exactly the same. And to show that I did change it, the inductor, the capacitor, the resistor, everything is exactly as we would expect because it's still the same impedance, just in a different order. Okay, so I put these in parallel with each other, and a lot did change. Our phase angle is moved the other direction. Our signal is actually a bit larger on the output. Not a lot larger. Again, we are dealing with a matter of millivolts compared to volts, but we do have a completely different look on our system. So this is actually referred to as a tank system. So what's happening is the capacitor is charging and discharging. At the same time, the inductor is, well, it's fluxing. You know, it's creating its reactance. And that's in parallel with the capacitor's reactance. And we'd add those the same way we would add resistances. So with the 6.28K in parallel with the 159 milliohms, we get a much less amount of actual reactance. But it is still inductive and capacitive, so they kind of are working against each other while at the same time providing alternate routes for the current to go through. So the reactants, same amount. How they're being added, that's what's changing. Because they're no longer in series, right, where one would go against the other. Now they're in parallel. There's a formula for that, which I do not want to get into, but it's very similar to the way you add parallel resistors. And it is really complicated, especially when you get into how we add the reactance. Let's just say the overall impedance of the system is slightly less. How much less? I don't even want to start doing the calculations for it. It's that much of a pain in the ass. But it's tremendously less than what it was when they're in series. Let me see. Well, I'll show you the outputs, and you'll be able to see for yourself. How's that? All right, and there's our output there, and you can see there's a bit of fluctuation there. That's just because I have cheap tools, but come on, you can do it. There we go. Very little bit of flux in the signal, and what it is really, this flux that you're seeing, it looks like it's on channel 1. This is actually happening with channel 2. It's just the way that everything is connected. It shows up as on channel 1, and that's mostly because of the way the scope works and how the grounds are connected. But you can see the flux, which it tends to appear to be going this way. It's actually going this way. Again, cheap tools give you cheap results, but it's a very low amount of flux going on there. And the changes that are happening have to do with the fact that we have a capacitor and we have an inductor. So they're in parallel with each other. So the capacitor is charging and discharging, and the inductor has a magnetic flux that's growing and collapsing. And this is causing the voltages to spike and to collapse and then go back up. So it gives a little bit of a crazy reaction of this setup. So you'll see periodically it'll go up and down. You see every once in a while it looks like the source voltage is less than the voltage going across the load, and that's perfectly acceptable and understandable given what we have. The inductor is going and the capacitors are going. It's creating a bit of a it's kind of a radio type thing, you know. This is similar to what you'd find in like an antenna, where you're trying to pinpoint a particular frequency. Now, if we find the right frequency, we can eliminate all the phase shift and all the reactance and have pure resistance, which is what we do when we adjust the radio knob to pick up a particular frequency on the radio. So this is very similar to radios. We don't spend a lot of time dealing with this particular circuit as far as calculating its impedance per se. We look more for the resonant frequency in this. So what we can do is take a look at the calculations and find the resonant frequency. Okay, so to calculate resonant frequency, it's actually very simple. So we have two formulas, one for capacitive reactance, one for inductive reactance. And all we really have to do is find the frequency where those two things are the same. Because inductive reactance is the opposite of capacitive reactance. When the two have the same value, they cancel each other out. They are what would be called complex conjugates of each other. So at resonant frequency, you're going to have the reactance of the inductor, which is 2 pi times the frequency times the inductance. So I'm going to say R is when 2 pi f L is equal to 1 over 2 pi FC. Now, this is what we have, right? So, what we need to do is we need to take these and kind of solve them for F. Now, we have the F over here is pretty much by itself, but not quite. So what we want to do is we're going to multiply both sides by 2 pi F. 2 pi, or no, we're going to divide both sides by the 2 pi F. 2 pi times the frequency. So, 2 pi times L. Sorry, we're trying to get F by itself. So we divide by 2 pi L. And we have to do it to both sides. So what that's going to give us is that F is equal to 1 over 4 pi squared F C L. Now, we still have this frequency in the bottom here, right? So we're going to have to multiply both sides times the frequency to get that off of there. And what we'll end up is with frequency squared is equal to 1 over 4 pi squared times C times L. Okay, like that. So we still want to get this frequency by itself. So what we'll do is we'll take the square root of both sides. So we'll take the square root of this, square root of that. And what that's going to give us is that frequency is equal to 1 over 2 pi times the square root of capacitance times the inductance. And that is our resonant frequency right there. So we're looking for the frequency. And so you'll notice really quickly that time isn't part of this equation, right? There's no instance of time at all. But frequency is 1 over time. And what that implies is that this 2 pi times the square root of CL is equal to some manner of time. Just food for thought, you know, it's not really anything that is important to the discussion, but it is something that you'll want to take into account. Now, our C is approximately 100 microfarads, and our L is approximately 100 millihenries. So we're going to get our handy dandy calculator out. And we're going to do 1 divided by 2 pi times the square root of 100 microfarads times 100 millihenries, and close those parentheses. So I'm showing 50.329 and some trailing decimals in there. So currently we've got a really high frequency going on, and we're seeing a reasonable amount of voltage drop going on. So let's see what happens when we get down to this frequency. I got 3 decimal points of actually I got quite a bit more. I have 2 decimal points for my frequency, so let's go to frequency. Five, 0, 3, 3. And so let's see here. Wow. Tremendous. We're showing virtually no phase angle, and the only voltage drop we have is what's going across the resistor. It's as if we put in the proper frequency. Let me go ahead and show you the scope here, and you can see for yourself. Okay, so here's the function generator, and as you can see, we have 50.32 hertz coming out and 5 volts peak to peak approximately. It's not exactly perfect, but here's our output. And as you can see, the peaks are lining up perfectly. There's a bit of a voltage drop, and that's because of the resistance that's going between the ground and the capacitor and the inductor, which is right here. You can see they are in parallel with each other in series with the resistance. Exactly what you would expect to be seeing here. So there you have it, the resonant frequency. This is the frequency at which the capacitive and inductive reactances cancel each other out perfectly. Not hard to find. Showed you how we came across the frequency and why it works so well. So if you've been watching so far, you should be pretty up to snuff on how we calculate impedances thus far, but we're not done yet. All right, so we've been talking about capacitors, resistors, inductors, how they work together to form impedance. Well, now we're going to look at the speaker, right? So this is rated at 8 ohm, 15 watt speaker. Great. Doesn't really tell us much of anything, but let's measure the 3 factors that we know. We know there's resistance, capacitance, and inductance. All 3 of those are in this component here. So let's start with the resistance. It's 8 ohm speaker, and it measures at 7.4 ohms. Let's write that down. Fluctuated 7.3, so let's write that down. 7.3. Where's my paper? .3 ohms. 8 ohm speaker. Now, the next most prevalent component of the impedance should be the inductance. Voice coil is essentially an inductor, and here we go. 99.4, 99.5, 99.6, 0.7, 0.6, 0.7. So we'll call that 99.7 since that's where it stops. So and these are micro henries. And oh, look at that, it went all the way up to 100. So yeah, 99.7, 100, close enough, right? Now let's look at the final component, capacitance. So getting between 12 and 13. It's kind of going all over the place, you know, not really wanting to settle down. 12.9, 13.8, 13.9, 12.8. So they're slowing down a bit. This is a difficult one to measure on a speaker because there is so much inductance in there. So the way it's fluctuating and fluttering around seems to be favoring about 13 microfarads. So we're going to go ahead and call it 13 microfarads. Now, I've talked about how to calculate these things, right? So I'm going to tell you how it's done. So this is done using a form of vector analysis, and what it is, it's using the Pythagorean theorem. And what it is it takes the resistance and considers it as like the base of the triangle. And then we use the capacitive reactance and the inductive reactance and the sum of those two to create the hypotenuse of the triangle. Then we use that, and the angle between those is what gives us our phase angle. So we have our formulas for capacitive reactance. We have our formula for inductive reactance. We're going to use those, and we're going to put them together. We're going to add them together, but because one is negative and one is positive, it's the difference between the two. So what we have is the square root of r squared times xl minus xc squared. And that's our formula right there. Very, very easy and simple to do. So the problem is we don't have a frequency to use. But if we look at these two things, remember we were able to find the resonant frequency. At the resonant frequency, the only resistive element is at 7.3 ohms, because XL and XC will be equal and opposite, giving them a value of 0. So we look at these, we'll look at, well, we already know what the resonant frequency what it'll be, but what about other frequencies, like frequency of the low E, right? That's somewhere around 86 hertz, so we'll just go 80 because I don't know it offhand. So we'll look at impedance at 80. What is that going to be? Well, we have our inductive reactance. It's going to be 2 pi times 80 times our 99.7 times 10 to the negative 6 is 0.05. So write that as 50.11 milliohms. And I didn't worry about the J factor. You know, we can worry about that when we actually calculate it, because it really just puts the J factor on there. So I could put it on there now or put it on there later. It doesn't matter. All right, so for the capacitive, we have 13 microfarads that we're going with. So we go to, oh, no, not 2. We go 1 over 2 pi times the frequency times our 13 microfarads. And that gives us 153.0335. So 153.03, and that's just regular ohms. It's actually got more capacitive inductance at this frequency than it does inductive, even though it's mostly an inductor, right? So we plug that into our frequency. We're going to get Z equals the square root of 7.3 squared plus XL, which is 50.11 milli with the J factor, minus the 153.03 with the J factor, and that is squared. So let's look at what is at the low end of the frequency spectrum. So square root 7.3 squared plus 50.11 times 10 to the negative 3, J factor, minus 153.03 J factor squared, and we get, wow, 152. That seems a bit off to me, right? 152? Well, I mean, there's a phase angle on there too, so. Let's try that again. Oh, almost forgot the J factors. Yeah, 152.8. You know what I'm doing? We still got it in polar form. Let me start over. All right, square root of 7.3 squared plus 50.11 times 10 to the negative third J minus 153.03 J squared. All right. 152.8. 0.81 if you want to be precise. 0.805617.5. 152 ohms. 52 ohms of impedance. But it's sold as an 8 ohm speaker. Why do you suppose that is? Well, let's check at a higher frequency. 80 is such a low frequency. So let's try the open A string, 110 hertz. So Z. Well, we gotta calculate again. So we'll do the L is equal to 2 pi times 110 times 99.7 times 10 to the negative 6. And we get 0.069. Nice. And there's a J factor on there, so keep that. And C. We're going to do 1 over 2 pi times frequency times 13 times 10 to the negative 6. And we get 110.297. So and there's a J factor. So same thing, right? We got the resistance doesn't change. So we have square root 7.3 squared plus 0.069 with the J minus 110.297 with the J, and we square that and we get 109. And this is all apparent. It's not actual resistance. This is apparent resistance. You can tell because it's got the J factor on there. We could look at how much of a phase angle there is, but you can see this this total impedance is not going to 8 at this frequency. Let's go to another frequency. Let's go let's do 440 hertz. So 1 over 2 pi times 440 times 13 times 10 to the negative 6. Okay, this is all coming out now for the capacitor. It's 27.8. So .8 XL would be 2 pi times 440 times 13 times 10 to the negative 6. And it's 0.035. Oh, 0.036. All right, same thing. Square root 7.3 squared plus 27.8 with a J minus 0.036 the J. Square that and we get 26.78. So 26.8. So, based on what we're able to see, the only time you're going to get close to just 8 ohms is going to be at that resonant frequency, which we can calculate based on its capacitance and reactance using the formula I just gave you earlier, the 1 over 2 pi times the square root of L times C. So let's see what that frequency is. 1 over 2 pi the square root of 99.7 times 10 to the negative 6 times 13 times 10 to the negative 6. And we get 5.04K. 5K. Rather high frequency for this particular speaker. Now, as you can see by looking at this, this is not a guitar speaker, right? This isn't something that you'd find in really any amplifier that you would be using yourself. This comes from actually a TV surround sound system, one of the rear speakers, not meant to be the main speaker in the sound system. It's a, what do you call it, the surround sound. So it's meant to have kind of a higher impedance than the system itself. But at 5K, the real high pitched sounds that would be maybe in the string section of a choir or something like that, those would come through here rather nicely. Lower frequencies are going to be a little bit muddled, but it is what it is, right? 8 ohm speaker though, measured at 7.3 ohms. 7.3 is nominal to 8. This whole idea that these speakers are based on their impedance when they're sold to you, it's not exactly true. You know, you'll see that some sites will have ratings where they'll show the DC resistance compared to the impedance. They're not really showing you the actual impedance of it because they're not specifying a frequency. They're just showing you a nominal rating. So nominally, this guy's got 8 ohms. Sure, it's nominal, 8 ohms. But as you can see by doing the calculations, it's nowhere near the 8 ohms of impedance at any frequency that you're going to be finding on your standard typical guitar. Now, in my other video, I'd shown this speaker here as having 8 ohms of DC resistance, and we can measure that again, no problem. Pop this right here. Rather than using my, I thought for sure that there'd be able to reach that, but no worries. So what do we got? Yeah, still the 7 point. It's kind of fluctuating a bit. Right now it's showing at 7.5. 7.5. Let's take a look. Oh, before I take a look at that, let me write that down so we'll have that. Let's see here. 7.5 ohms resistive. All right. Now I'll pull out the LCR meter here. And looks like we got 187.5. Those are microhenries. L goes 187.5 microhenries. And lastly, but not least, capacitance. Now this one I'm expecting to be pretty low, but who knows? I've expected a lot of things that have turned out different than I was expecting. All right, so this is interesting. It's actually giving me a negative number. So because it's giving me a negative number, I can't really use that. I have to assume that it's essentially zero. The reason why is because the way the meters work is they use the frequencies you could hear that was coming through there, and it measures the amount that it gets from that frequency and uses that. And because it's coming up negative, means that it's so inductive that the capacitance that's within it, the straight capacitance, which was rather large in the other speaker, it's not enough to even be measured with all that induction. So we'll call that zero. Make our math a bit easier if you think about it, but still, it is what it is, right? So equals zero. So, same equations, right? We gotta pick a frequency, and we'll use the same frequencies we used. We used 80, 110, 440. Now, just so you know, because the capacitance is zero, we're not going to include that into the equation because 1 over 0 is an indefinite number, and if you plug it into a calculator, it's going to be either 0 or negative 0 or infinity or negative infinity. It's best just to use 0. Trust me, you don't want to try to play with that game. So at 80, our inductance, we have 187.5 microhenries. So 2 pi times our frequency of 80 times 187.5 times 10 to the negative 6 equals 0.094. That's 0.247777961 times 10 to the negative 3, so 0.0094, and plug that into our equation. 7.5 squared plus, and I'm just going to use the answer key to take this answer, put it in there, add my J factor, and forgot the parentheses. And square that, and let's see, go to what? Why are you giving me so much grief? All right, try that again. So we have 2 pi times 80 for our frequency times 187.5 times 10 to the negative 6. Now let's put the J factor there. All right. 0.09424777961 blah blah blah. Square root of 7.5 squared plus the answer squared equals 7.4994078. Essentially 7.5. It's actually a little bit less than the 7.5 that we had measured. So at 80 we have 7.5 ohms. You'll notice that the J factor has virtually disappeared because, well, such a small amount. So next up on the agenda, 110 hertz. So we're going to calculate that. We got 2 pi times 110 times the 187.5 then negative 6. J factor. All right. That is 0.129590697. So still a very small number, right? And we're going to go through and we're going to do the same thing. 7.5 squared plus our answer squared 7.498880333. Essentially 7.5. All right, now let's try 440 hertz. So we have 2 pi times 440 times our inductance, which is 187.5 micro. And our J factor. And that's going to give us 0.51836278878. So about a little over a half an ohm. So let's see what that works out to on our equation. 7.5 squared plus our answer squared 7.482065. So as you can see, as we go up higher in frequency, our impedance is actually getting less and less. It's because this J factor works as a negative number, and if you've ever seen a Smith chart, you can use a Smith chart and you can see how these impedances work, but it's putting a phase angle on it, and using a unit circle, you can see that a phase angle will affect the x value whenever you're anywhere off from the 0 degrees. So each time we do this, it's getting a little bit more of a phase angle, even though it's not enough to register on here as far as anything. Hold on, I can change our mode, see if we can see if there's any phase angle on there. So let's see, 7.5 squared plus 8.78. Okay, so the phase angle is so small that it's not even showing as 0. It's a very small phase angle, so less than 1 degree. Unless I've got it in degree mode, so it's less than 1 degree. I could change it to radians. Maybe it'll show radians. Radians are 1 degree. 360. So yeah, it's going to be essentially 0 radians as well. So very, very small phase angle. And this is all the way up to 440 hertz, right? Yeah, 440 hertz. So 7.482065224. So essentially 7.5 ohms. So what this is telling us is that our speakers being sold to us at a nominal impedance of 8 ohms, if it measures 7.5 ohms, probably going to have 7.5 ohms of impedance. Not really a lot of wiggle room when you're dealing with that. It is what it is, right? It's a coil of resistance that has some inductance, and we refer to it as impedance because we use it with an alternating current. It's impedance. The thing about that is, even if we were just using resistors, right? Resistors, they have a resistance of this one, I think is around 100K. And 99.6K. This has impedance. Has impedance of 99.6K ohms. The resistance, the impedance, they are very much related. And yeah, they may not be exactly the same, but when you're discussing impedance without discussing frequency, you are either referring to a DC resistance of 0 hertz, or you're talking about equivalent series resistance taking into account a reference frequency. That's it. There's nothing hidden in anybody's agenda about anything. So the speaker here, it's an 8 ohm speaker. We did the calculations for its impedance. And through most of the audio spectrum, this thing has got incredibly high impedance. Until you get up to above, like probably around 4K, you'd start to notice a bit of a drop, but it doesn't get to this 8 ohms until you get close to 5K. Otherwise, it's got hundreds of ohms. Hundreds of apparent ohms. It's not going to have power loss across that. Power loss is only going to happen across the resistive elements. And that's where things start getting complicated. Now, I think I've gone into this enough that you can see that Detroit Record doesn't know what the fuck he's talking about when he starts talking about different people referring to things by different things and acting as if he's some kind of authority on really anything at all. Now, I'm not a guitar player, right? I've said that more than once. But based on the things that I've seen from Detroit Record, I probably know more about playing guitar than he does. And that's saying something, right? Because I don't really know shit about playing guitar, right? I know what I've read, and I've seen a few videos that I've picked up a few things from, but not really anything that would say that I have any kind of knowledge on the subject. Now, I could talk about tuning of the guitar. I know that, right? E, A, D, G, B, E. Yeah, right off the top of my head that came. And I know about intervals, right? The distance between notes in a scale. I know about scale degrees, right? Like the major scale, which is really the only scale I know, is the C major and the G major. Other than that, I don't fucking know, right? But I know that C to D, that's one scale degree, goes from the first to the second. D to E goes from first, second, third. C, D, E, F. 1, 2, 3, 4. And you'll remember in Will's video, he was saying that we want to look at the E string as being an F and the B string being a C. C, D, E, F. 1, 2, 3, 4. C, D, E, F, G. Fifth, right? And he was wanting to go from the B to G, which is going down in pitch, right? Well, if we go from G, F, E, D, yeah, seems counterintuitive because he's talking about going from G to C. G, F, E, D, C. But we don't go F, E, because you're saying E to B is supposed to be a fifth, right? But if we're going down, F, E, D, C. So he's missing it, right? He's missing it because that's not the interval. It is a fourth, not a fifth. So people will oftentimes confuse intervals and scale degrees. So if we're in the key of C, D, E, F, G, A, B, C is the octave, goes back to 1. So if C, D, E, F, G, A, B, C, blah, blah, blah. So in this instance, when we're talking about the C scale, C, D, E, F, G, G is the fifth. It's the fifth scale degree. But when we're talking about intervals between strings, well, C isn't a string, right? It's not. And we know that the G to B is a major third, so we'll skip that one for now. We'll go from B to E. B, C, D, E. It's fourth. E, D, C, B. It's a fourth. These are intervals, not scale degrees. We're not looking at the E major scale and saying, well, what's the fifth of E? We're looking at the distance between the B string and the E string. Another one to look at would be the E string to the A string. E, F, G, A, B. Right? So the E to A string, you're looking at the distance between them, it's a fourth. Scale degree, you're talking a different story, right? Because you're talking about he's talking about, I guess, the A scale going to the E string, then yeah, that would be a fifth. E is the fifth of A. No question there. But that's not the interval between the strings. That's the scale degree of the A scale. And when you're talking fourths and fifths, it doesn't matter if you're talking major or minor, because fourths and fifths are the same for majors and minors. That's why they're called perfect. I think it's a dumb name, but who am I, right? But this concludes all of our lessons on impedance. If you have any other questions about impedance, definitely feel free to comment down below. Nobody is blocked on my channel. As far as I know, nobody's ever mentioned me in any way because I am such a small channel. I don't have subscribers. I don't have views. So these people that Detroit Record's talking about laughing at me, I don't see how that could be happening since nobody really knows I exist, right? I mean, for them to be able to laugh at me, they'd have to see my video, which means I'd have more views. For them to be able to see my video, they'd have to have at some point subscribed to my channel, which means I'd have some subscribers. I have neither subscribers nor views. Matter of fact, I have one video that, or I guess two videos that have a substantial number of views, and they're both talking about a certain circuit, right? Nothing to do with amplifiers or guitars or anything like that, just a fucking circuit that I built. So there's two things that you should know. Number one, Detroit Record doesn't know what the fuck he's talking about. And number two, Detroit Record lies a lot. And he lies for no reason. You know, he's not gaining anything by lying about me or anybody else. He's just doing it because, well, it's what he does, right? It's the conservative playbook. Tell lies until they become true. Now, I've talked a lot about a lot of different things in this video and carrying on for quite a bit now. So I'm going to go ahead and end it now. Thank you for watching. Have a great day.